Now it's recording.
It's recording? Great.
We can start.
All right, thank you very much for the introduction, Professor Hammond. So as she said, I'm Dr. TJ Hammond. I've been a professor here for a few years. I have a small group going. I don't have any pictures of my group. We don't have anything updated because normally we have taken pictures over the summer, and of course everything was shut down then. So unfortunately, I don't have any pictures of my group, but I have currently 2 graduate students and about 3 or 4 undergraduates working in my lab. I already have plans for next year for another graduate student. So if you're interested in working with me, I would be happy to be able to work with you. So my title of my talk is Ultrafast and ultrasmall, manipulating individual electron motion. And that's more of a long-term dream, I suppose, of what we actually want to do. We can control collective electron motion, and we're in the process of getting it down to dozens of electrons. So we're not quite at the individual electron motion yet, but that's kind of the goal of my research. So when I talk about ultrafast, I mean something on the order of femtoseconds and attoseconds, and these are probably words that you probably don't know off the top of your head. So let me introduce to you the ideas of attosecond science and femtosecond science. So attoscience is studying effects on an attosecond time scale. So that an attosecond is something that's really, really fast. So what is an attosecond? Well, if you have, can you see my pointer here? Maybe if I don't know if I have I guess I just have a pointer. But if we have the Earth orbiting around the sun, this takes about 3.15 times 10 to the 7 seconds, so on the order of millions of seconds, so megaseconds. And the distance of the Earth to the sun is on the order of gigameters. It's 0.18 or 0.15 gigameters, plus or minus. And so this is kind of scales of a planet orbiting around the sun. Megaseconds and gigameters. But of course, on the smaller side, we have microprocessors. So microprocessors are called microprocessors because they used to have wires that were about the size of micrometers, and the transistors and stuff like that on orders of microns. Now they're down to the order of nanometers, something like 10 nanometers or so. Is I think where Intel is kind of having problems right now, but they're around 10 nanometers. And these transistors can turn on and off in about nanoseconds. And so when you buy like a new computer, you see something that says like, 3 gigahertz or 4 gigahertz or something like that. That means that that's how fast these processes can happen is, you can do a few of these processes in a nanosecond. But if you get even smaller still, then what we have is, a molecule here. So this would be something like a CO2 molecule. And this is going to be the size of a few nanometers. And this thing can rotate on itself on the order of picoseconds. It's something like 10 picoseconds or so. So 10 picoseconds, it's on a picosecond is 10 to the minus 12 nanometers, 10 to the minus 9. And so these things are becoming increasingly decreasing in size. So they're smaller and smaller, and they're getting faster and faster. And then you have this CO2 molecule can also vibrate. So you can have this bending mode or this stretching mode, and the amplitude of these modes is on the order of an angstrom, so 0.1 nanometer, and they take about 50 femtoseconds or so. So a femtosecond being 10 to the minus 10 to the minus 15 seconds. But if instead of we replace the Earth with an electron and the sun with a proton, this would be our hydrogen atom, and this is a classical Bohr atom. And this is something that as an undergrad, you should probably learn, in first year or maybe even in high school, that it's not a very accurate representation of what's going on, but it gets kind of the gist of what's happening inside of an atom, at least inside of a hydrogen atom. And this electron would orbit around in about 150 attoseconds or so. So an attosecond is 10 to the minus 18 seconds. So it's 1 billionth of 1 billionth of a second, or a billion times faster than a nanosecond. And this radius here is something like half an angstrom, or 53 picometers. So the outline of my research is trying to generate these ultra short pulses. So how do we get really, really short pulses so that we can actually make these measurements? and how do we measure these ultra short pulses. And I'll talk about how we generate attosecond, how we can generate these attosecond pulses, and how we can make attosecond changes to the waveform. And I'll finish with some spectroscopy and something we'll be starting really soon, which is called attonanoscopy, which will be time resolved spectroscopy at the nanoscale. So why do we want to actually make a really short pulse? Well, a laser pulse can actually act as a shutter. So Edward Muybridge took these series of pictures in 1878, and it was actually to settle a bet. I kind of love the fact that this new technology was basically the governor of California at the time, who was Stanford, which is what Stanford University is named after, was really, really rich, and he had a bunch of horses, and he wanted to know if a horse was galloping, whether it actually lifted up all of its hooves off the ground, or if one was always stationary. And so he bet somebody, some money, and to settle the bet, he hired this person, Edward Muybridge, to record a series of images on a track. And so this is the first time somebody ever took a series of camera images and strung them together to be able to make a movie. Now, MIT, about 130 years later, can now actually have a shutter that's so fast that you can actually have a light pulse. And this is a real object. This is some cylinder and an apple, and it's actually a light pulse that's propagating through this lab, and they can actually take this shutter is so fast they can actually see a light pulse propagating through and bouncing off of this material. So that's the idea of why we want to have a short laser pulse, is that a laser pulse can act as a shutter. A laser pulse can come in and excite some molecule or an atom or a crystal or something like that. And when it excites that can act as a shutter for what we're trying to do. It can be a start or a stop of this experiment. So if we have a really short pulse, we can have really high peak intensity. So the other thing that's really nice about this is kind of like a flash on a camera. On your cell phone, when you're trying to take a picture in the dark, you can't have like the light on all the time. It's really tough to do that. But it's really easy to take a picture with like a bright flash. And so you can have a really bright flash and it doesn't take too much energy. And so having a really high peak intensity allows you to have a lot of energy deposited in a short amount of time, but you don't need to draw a lot of power. You can also deposit a lot less thermal energy. So on the right here, it's two pieces of metal. I think it's steel. And if you have on the right a 50 picosecond pulse, so a few weeks ago, just before the break, Dr. Razy was giving a talk on his lasers, which are picosecond lasers, that he ends up ablating material with these picosecond lasers, or nanosecond lasers, I suppose. But he wants to do that because he actually wants to, melt and destroy this material. But that's what happens, right? This pulse is on for so long that these electrons get shook around or get shaken, and they end up melting as they get ablated. Whereas if you come in with a 60 femtosecond pulse, so in the femtosecond regime, so 3 orders of magnitude faster, the material can't melt. And so when you ablate, you actually don't deposit any material to any energy to the material. The material actually just flies away as this ionized kind of material. So you don't actually deposit energy to the material, which is very beneficial if you're trying to do like some kind of like nano machining or something like that, or micro machining. And so of course, we actually want to do attosecond science with this. And so if we have an attosecond pulse, we can have attosecond temporal resolution. So how do you make a really short laser pulse? So as an undergrad, you might have seen this before. So it deals with the Fourier transform. But even if you're not familiar with the words Fourier transform, you probably have heard of the Heisenberg uncertainty principle. And so the Heisenberg uncertainty principle is that if you know the position of a particle really, really well, then you can't know its momentum very well. And likewise, if you know its momentum very well, then you can't know its position very well. Well, this is the exact same thing, just reiterated in terms of energy and frequency, but or energy and time. So if you don't know its energy very well, and so we call energy, as you might know, energy is related to the frequency of a light particle. If you know the energy very well, then you can't know its time very well. And likewise, if you know its time very well, then you can't know its energy very well. And that's the same thing that's going on with these laser pulses. If we have a really narrow spectrum, so a really small distribution of energy of our laser, then we end up having a really, really long laser pulse. Conversely, if we have a really broad spectrum here that spans, basically all of the visible, so this would be all the way from the red up to the blue, then this leads to a really, really short pulse. And so what we want to have is a really, really short pulse. So we need to have an extremely broad spectrum to be able to create these really short laser pulses. But that's not the full story. You can actually also have, there's a thing called spectral phase. And so if you have a non-zero spectral phase, then you can end up with this same spectrum here, but it can also lead to a long pulse if each of these frequency components that make up this pulse are dispersed. And so what I mean by dispersion is you come in here with, say, white light hitting a prism, and this thing spatially disperses this beam. So the index of refraction of the material is frequency dependent. And so that means by Snell's law that the angle that this beam, that the different colors come out at, is going to be different. And so red the index of refraction of glass is lower in red, and so this beam deflects less. But the index of refraction of purple is higher, or indigo, I guess, or violet is higher, and so that means it refracts more. And so the index of refraction is then, we can see the index of refraction change by the spatial dispersion of a beam. But the same thing happens to this laser pulse as it passes through glass. But instead of only being spatially dispersed, we would actually be also temporally dispersed. So it also gets dispersed in time. And that's exactly what I'm showing here in this kind of rainbow thing. And this pulse here is called, it's said to be chirped. And it kind of sounds like a bird. I don't know if I'll be able to whistle at this time, I'm not very good at it, but maybe you can do it on your own, that you start off with these low frequencies and you end with these high frequencies, and it goes something like that. I don't whistle very well, but it would be something along those lines, right? So you can do that on your own, but changing that frequency as a function of time is called a chirp. And it's because that's what birds do, that's what radar does, and that's what laser beams also do. So if you want to have a really short laser pulse, you need to have a really, really broad spectrum, and you also need to carefully control this phase. But how do we create these really, really short laser pulses? If we come in with a laser pulse that's, say, this long, how do we take this long laser pulse and make it into become this short laser pulse? So I can describe this kind of pictorially or with equations. So if you like pictures like me, we can describe it this way. So if you have in free space, you have an electromagnetic wave, and you've probably seen this before, that an electromagnetic wave oscillates up and down. It's this transverse wave. And so the electric field here is in red, and it's oscillating up and down in space, and also in time, because it's propagating through space at the speed of light. But if you have a wave hitting material, then that material, of course, is going to be made up of charged particles. And don't forget, an electromagnetic wave is going to be a force, the force given by the electric field times the charge that it's hitting. There's also going to be, of course, in the Lorentz force, there's also going to be the velocity of the particle times the cross product of the magnetic field. But it turns out that the magnetic field is actually going to be 3 times 10 to the 8th smaller, so 300 million times smaller than the electric field. And the reason for that is because it's divided by the speed of light. So in any case, the force is going to be strongly dominated by the electric field on this charge. And so what that means is we have an electron that's sitting in some material. It could be in a gas, it could be in a solid, whatever. And this electromagnetic wave is oscillating up and down, and it's forcing this electron to move up and down. And that's actually what happens every time you have light hitting anything. It happens when, it's hitting my face so that you can see me. It's happening, when you look out the window and you have light refraction. So, the sunlight coming in and it bends slightly when it goes through the glass. That's actually what's going on in the glass, is all these electrons are conspiring together to change the direction of this light and slow it down. Now, what happens instead of having linear optics? So that's the principle of linear optics. If we have nonlinear optics, and so if you look on your right, it might be that the zoom image is there, so maybe you have to move that. But the what you have on the right is if we have a really strong field and we end up having an anharmonic response. So a harmonic response would be the top one. So this electron oscillates up and down, nice in a harmonic motion, just like we had this wave in free space. But if instead, for some reason, this electron oscillates anharmonically, what you generate are new frequency components. And those new frequency components would be, say, like here, this is the second harmonic generation. So what you actually do is these photons here that are oscillating, that are forcing this electron up and down, here it's forcing this electron up and down, but for some reason this electron isn't going down in a harmonic way, and that generates second harmonic. And so what you do from a quantum mechanics perspective is you actually take two photons of this red light and you destroy them, and you then create one photon of this blue light. And that's called second harmonic generation, because you've destroyed two red photons and you've created one blue photon. And if you had a spectrum of this, it would look something like this, where you have your red spectrum is really bright, and then you have this kind of weaker second harmonic spectrum. It's not very efficient. You know, this isn't 100%. We don't convert 100% of these photons over to here. We know if we're doing a good job, it's something like 10 to 20% is a pretty good job for second harmonic. But basically, in summary, is a field pushes around a charge, an electron is going to be that charge that gets pushed around. But from Maxwell's equations, it's really, really important to understand that also an accelerating charge also radiates. And so that dynamics of what's going on with this field pushing around this charge, but then this charge responding in this way, and causes a radiation, that radiation ends up being of new frequency components. So we can also talk about this mathematically. So we have, you know, the second order partial differential equation. And so for those people who have taken E&M or are going to be in my electromagnetic waves course, I'll talk about these equations. And so if you like math, we can describe it mathematically, or you can do it pictorially, which is what I just did. But how do you create even more frequency components? And so what we can do is another way is, this is called self-phase modulation. And this is an even higher order process, so you need an even stronger laser to be able to do this. But if you like pictures, you can describe it this way. So any field pulse can be described in terms of its amplitude, which is going to be this blue outline here, this envelope, and its phase, which is this green oscillating thing. So this, you know, oscillates up and down with some sinusoidal phase. And, you know, as you probably know, that you know, cosine and sine can be represented by complex notation. E to the I phi is, you know, cosine phi plus I sine phi. So what you have is this envelope given in blue. And so just for this diagram here, it's a Gaussian envelope. And then what we have is a, you know, it's oscillating phase. And the energy for this is going to be constant in time. But what we do is we focus this beam. It's in a very powerful, you know, it's very intense pulse, high energy, and we focus it very tightly into, say, some material like a piece of glass. And what we get out is we actually create new colors. And what happens is this pulse becomes really chirped like what we saw before, but it gets chirped in a really weird way. You see that the longer wavelengths are at the beginning of the pulse, and then the higher frequencies are at the end of the pulse. So it still has that, you know, that chirp like before, that like we saw before, but that's only over a certain region of this. It's not over the entire pulse. It's kind of this weird shape. So what that means is that we've created new frequency components. So this energy now is changing as a function of time. So we have new frequency components, but these new frequency components aren't controlled in phase, and so we need to control these frequency components in phase. And if we do that, we can compress this pulse, and that's what that looks like here. And this is called a single cycle pulse, and the reason for that is because from here to here is basically the envelope of this pulse. And so that's kind of the goal of people working in attosecond science, is we really want to make these really short pulses. You can think about this in an alternative way if you want to think about this in terms of frequency space. As I mentioned before, you know, we have this time frequency correspondence from the Heisenberg uncertainty principle. So anything that we talk about in terms of time can also be talked about in terms of frequency. So this would be a description of this pulse in terms of time, but we can also describe it in terms of frequency. And basically what we have is a pulse here that has a spectrum here. And as this propagates through this material, these short wavelengths create more short wavelengths, and these long wavelengths create more long wavelengths until we get more and more and more until this creates a really, really broad spectrum. For those of you who like math, these are the partial difference equations that you have to solve. This is kind of the basics of it. It gets far more complicated even than this. So in order to quantify it, you need to actually solve all these differential equations, and that's what I needed to do to actually simulate this here. But pictorially, this is what's going on to explain the physics. And this is more math to explain some of these nonlinearities and stuff like that. But what this math tells us is the nonlinear response that's given by this N2 here, then how much this glass is going to be responding in a nonlinear way is going to be able to create more and more frequencies. Also, the more intense the pulse, so the more powerful we have this laser, the more new frequencies we can create. And also the shorter the pulse that we have, we can create even more new frequencies. So it's actually beneficial to us. So as I said, we want to have the shortest pulse possible, means we need to have the broadest bandwidth possible. And it turns out that if we have a short pulse, we can more easily make a shorter pulse. That only works for a certain, for so far, but you can actually create a really, really short pulse this way. And so this is what you need to do in order to create these really short pulses. And so I asked also, how do you, but how do you control this phase? You have to compress this pulse. So what comes out ends up being long. You need to make this pulse short. And so how do you do this? Well, you can get these really, really fancy gratings, and you can see you have all these people here in these suits. I guess before COVID, this would be more of a surprise, but now basically everybody wears this all the time. But basically you need to make sure that there's no dust on any of these gratings. So these gratings are big. They're something like 3 feet wide by 1.5 feet tall. Each one costs, I can't remember, $50,000, $60,000 or something like that. They're extremely hard to make. They're extremely expensive. It takes a lot of really, really advanced technical know-how of how to make these things. But they can compress these pulses really well. You can also do it with prisms. So as I mentioned before, you have white light coming in and a prism disperses this. This prism disperses it in such a way that if you have these 4 prisms set up properly, that what comes in is going to be this chirped pulse, and what goes out is going to be this compressed pulse. And so it's a good understanding of how spatial and temporal pulses are coupled. You can also do this with fancy mirrors. So this is what we do in our lab right now, is we come in and we have these fancy mirrors specially designed to be able to compress these pulses. So you come in with some pulse that's shaped like this, like red to blue, it's chirped. And then you design it so that the front of the mirror reflects shorter wavelengths and the back of the mirror reflects longer wavelengths, and that compresses the pulse as well. And understanding this stuff and being able to build lasers around this led to a Nobel Prize from a Canadian, Donna Strickland, who is a professor at the University of Waterloo. She was actually, so Professor Rangan, when she introduced me, said that I had worked in University of Ottawa. As a postdoc, Donna Strickland, it was her first, her postdoc was the first postdoc in the group that I worked at in Ottawa. And so there have been some very impressive people who worked there before me. Yeah, her work's extremely impressive. So what her work on was actually her PhD project was making chirp pulse amplification. This is what led to the Nobel Prize in 2018. Was they came in with a short pulse oscillator. So a laser itself doesn't produce very intense pulses. These tend to be very short, but they can't be that intense. And so what you do is you take this pulse and then you put it through a grating, like a grating pair. And instead of having the pulse actually compressed, if the pulse is already coming out of the laser compressed, then you pass it through a series of gratings, then it actually stretches it out. And so what they do is they set these gratings up in a special way so that the pulse is stretched out by a lot, by something like 10,000 times or 1,000,000 times or something like that. And what that allows for is the peak intensity ends up being much, much lower. You pass that. So this pulse is now stretched out. You pass it into this power amplifier, and because you've stretched out this pulse by about 1,000,000 times, you can amplify this pulse by about 1,000,000 times. And the thing is that that's one reason why an oscillator, a laser oscillator, can't produce very intense pulses, is because you'll actually destroy the material that is making the laser itself. So if you have some kind of crystal or something like that, it can only handle so much intensity. And so if you tried to take out too much energy from this crystal, then it'll actually break itself. And so you can't run this for very long. So what they do is then they break this up into multiple steps. So they take this weak pulse and then they amplify it. They stretch it out by 1,000,000 times and then they amplify it by 1,000,000 times, or something on that order. And now this pulse is stretched out and hugely amplified. And then you get these really, really big gratings. And that's what these big gratings are here for, is because these gratings, even though they reflect like 99% of the light, that 0.1% or that 1% of the light that they absorb is enough to damage these gratings. So they have to be really, really big to be able to have these really intense beams. But they recompress, and then you end up with a really intense pulse coming out on the right here. So that's something that I was working with and something that we work with now in my lab. And so what we wanted to do is try and make attosecond pulses out of these short laser pulses. And so, as I said, if you have a short pulse, and so that's what's shown here. So we have this laser beam here that's propagating to the right into hitting this quartz plate. And so that's kind of a two-dimensional cross-section of this is shown here. So we have in time on the horizontal axis and vertical axis, we have the radius of this beam. So it's Gaussian pretty much in time, and it's also Gaussian in space. And what happens is that this field is really, really strong, and it interacts. It's really short already. As I said, if you have a short pulse, you can actually make even more frequency components from a short pulse. So you have this pulse interacting with this quartz plate, and it actually creates more frequency components. But also, as you'll notice, you see this kind of weird shape of this wavefront. So these wavefronts were flat here, but now you see that these wavefronts are actually curved. And if you have a curved wavefront, what that actually means is that's the same thing that happens when you pass a beam through a lens, is that it actually shapes that wavefront, and that wavefront actually then means that this beam is going to be focusing. And that's exactly what we have here, is as this beam propagates, this intense part ends up coming to a focus. And so if we take a cross section of this, the original pulse is shown in blue, and then this beam at the focus is shown in black. That's the envelope, and you can actually see the field is given by this green dotted line, which is much, much shorter. And so this blue curve is something about 10 femtoseconds in duration, and this green dotted line is about 1 femtosecond in duration. And I managed to measure this, and so this resulted in a Nature Photonics paper, which is measuring this electric field, and you can see that there's not much going on, and then you kind of have this one sharp dip here, and we can reconstruct the electric field from that, and that's this. And if we square that to get the intensity, that is shown here on the bottom right, where you have 1/2 cycle that is extremely narrow, and it's around 1 femtosecond. It's not quite on the attosecond regime yet. It's on the order of like 1,000 attoseconds, but it's really, really short. And it's really hard to make optical pulses any shorter than that. So how do we make an even shorter pulse? How do we make an attosecond pulse? So this is with high harmonic generation. This is what Dr. Rangan had referred to when she said that I was working in a group with high harmonic generation. And what it takes is it takes a really, really intense laser beam to hit some material. And so if we think about what the potential looks like of, say, an atom, so this electron is sitting in some atom, so this is, say, like a hydrogen atom. This potential, as you know from Coulomb's law, the force of this electron is going to be 1/r², and so the potential is going to be 1/r. So that's what we have here, this cross-section of this atom, so the potential of this is proportional to 1 over the absolute value of x, because it's 1/r. What we have is this potential could be something in terms of and in terms of electron volts, would be something like 13 to 15 electron volts. So for hydrogen atom, it's 13.6 electron volts. And our photon energy is going to be on the order of 1 to 2 electron volts. And so that means that we can't ionize by a single photon. We can't take this electron up to this energy state, to the ionization potential, with a single photon. What we need to do is actually combine a whole bunch of photons. And if you remember from before, when I talked about second harmonic generation, we took 2 photons and destroyed those 2 to create 1 photon of second harmonic. It's basically what we do here is we take 1, 2, 3, 4, 5, 6 photons, we combine those to create enough energy so that this electron actually can go to the ionization potential. So instead of creating new frequencies, we've actually separated this electron from its parent atom. What this looks like, though, is if you have a laser field, then as I said before, you have this electric field is oscillating up and down, and so that means this force is oscillating up and down. Or if you integrate this to get the potential, then that means that you have this potential is negative E times X. And so you have this atomic potential like we had before, and then we've distorted this potential with this laser field. And so that's why this thing is now bent, is because we have a really, really strong laser field, and this laser field also applies a potential to this electron, and this electron also feels the atomic potential. And so it's this conflict between this laser potential and this atomic potential that leads to this distorted thing. But now there is a possibility, if you've studied quantum mechanics, that this electron can tunnel from where it used to be sitting to out in the open, which would be over here. And so how long does it take to tunnel? And this has been a question that people have been asking for a little while now. Theoretically, people have been discussing this since the 30s, but experimentally, people have been able to access this for about a decade or so. And it's still not really well understood. I think from a theorist standpoint, they would say it's well understood and the tunneling time is 0. It's not a very good question, but experimentalists can actually measure something. And so that means that maybe there's a disagreement between experiments and theorists. But in actuality, the tunneling time is imaginary, and so it shouldn't take any time at all in real time, but you could say it takes an imaginary amount of time, which is its own kind of confusing idea. But that's theoretical physics for you. So this electron can then tunnel out, so now it can be simultaneously in this parent atom and tunneled out of this, tunneled out into the continuum, out into free space. And so it's actually, you split this electron apart by allowing it to tunnel, and it doesn't have 100% tunneling probability, so it's in superposition state of being tunneled and still being with the atom. But the part that tunneled will be driven away, and then eventually, because it's an oscillating laser field, this thing oscillates, it drives one way and then oscillates, drives back the other way, and that will pull the electron back in. And when that pulls this electron back to the parent ion, it will then release this photon, and this photon E gamma will be huge. It creates really high harmonics. I've been generating, when I was a postdoc, I was generating harmonics up to 500th order or something like that. But some people have generated up to like the 5,000th order. You can generate really, really high harmonics this way. So I talked before about second harmonic generation. This is a way of generating like hundreds of harmonics. But in order to do that, you need to have really, really strong lasers. This isn't something you can do with just a light bulb. What does this experiment kind of look like? Well, what you would do is you would come in with this laser pulse that looks something like this. So on the order of hundreds of microjoules. So each individual pulse isn't all that intense, but it's 100 microjoules in something like 5 or 10 femtoseconds. And the central wavelength is kind of in the visible or near infrared. So visible wavelengths are on the order of 400 to 700 nanometers. Near infrared is on the order of 700 nanometers to about 2 microns or something like that. So that's typically the lasers that we use. We focus this into a gas jet. And so this is kind of a crazy setup, but this is the best way to do it. The harmonics that we generate actually don't propagate in air. I know that sounds kind of weird because you always see in light that everything can propagate. It turns out outside of the visible spectrum, things don't propagate all that well in air. UV, you might recognize from having the ozone layer. UV doesn't propagate very well in O3, so in ozone, but you can have other molecules and things like that that also absorb. And the higher energy you go into, the extreme ultraviolet, so on the order of like the 100th harmonic or so, gets really, really strongly absorbed in air. And so you need this to be in a vacuum chamber. However, you need something to be generating these harmonics. And so the easiest way to do this is actually with a gas. And so you're pumping gas into this vacuum chamber, then pumping this vacuum chamber out as fast as possible, which is kind of crazy. I assure you, I see how crazy that is. So it becomes really expensive because in order to have really bright sources, you need to have a lot of gas, and then that means that you need to have a really large vacuum chamber, and you need to have some really good pumps to pump this out. But you do that, and the light comes through, and you also create the infrared radiation passes through, the visible light passes through, and you also create these high harmonics, and then you can have a really, really thin metal filter, and these are extremely thin, like 50 nanometers thick. They're, you know, very, very fragile, but they reflect the visible light, but they actually transmit infrared, or they transmit extreme ultraviolet and X-ray light, and then you hit it off of a grating, and that causes this spatial separation of these harmonics, and we can observe these things. So that is how you would create these things. And so what that means is we have these really, really strong fields manipulating electrons in these potentials. And so what does this look like? So this is a quantum mechanical simulation, a 2D simulation of having this potential. So we have this dip here, which is on the right, the atomic potential. And then we have this thing that's oscillating back and forth, and that's going to be our laser field. And as you see, so we'll see when this thing comes back, that you have this initial wave function. So it's sitting kind of like, you know, like a hydrogen atom, it's sitting as this 1/r wave function. And then as we apply this stronger and stronger laser potential, a little bit of this electron wave packet gets leaked out. And as it leaks out and comes back and forth, it interferes with that other wave packet. And so that interference is what causes this high harmonic generation. And this thing happens back and forth and back and forth. And you can see this interference in terms of, you know, looking at this wave packet as a function of time, and you can see this interference coming up here, where this blue line here is our electric field. Now, what does the spectrum look like? Well, if we have this wave function oscillating back and forth, then we have a rapidly accelerating charge. And as I said back at the beginning, if you have a rapidly accelerating charge, that's going to produce radiation. Well, what that means is, if you look at this in terms of a spectrum, what you get are these series of bursts. So every time this is kind of intense enough that you have a large number of these electrons, or this electron wave packet, going away and coming back and interfering, and going away, coming back and interfering, going away, coming back, going away, coming back, you get these bursts. And each of these bursts here are attosecond pulses. They're about 50 attoseconds in time or so. And so you get these series of these attosecond bursts. And this is what a spectrum of one looks like. But if you combine all these together, then you get the overall spectrum, and it looks something like this. And so this is the harmonic order here on the horizontal axis. And you can see that this part here would be visible. And then we get into the extreme ultraviolet, and then there's even a tail getting into the X-ray. And so this is how we can generate coherent XUV, coherent ultraviolet and X-ray light, is with high harmonic generation. And these will be a series of attosecond bursts. But as I said, I want an isolated attosecond pulse. So how do we do that? Well, we again have a simulation here. What we do is we have this potential that's rocking around and rocking around. So it's going around in a circle. And if that's happening, these electrons aren't coming back. But then on one half cycle, we do make it come back, and then we make it go around and around and around. And this requires a fair amount of understanding coherent control and coherent processes. And so what we can show here is what the electric field looks like. And it looks kind of like this pigtail, in that it's going around in a circle, and then for one half cycle we stop and we go back the other direction, and then it goes back the other way. And so for one half of this pulse, it's going, say, counterclockwise, and then the rest of the pulse, it's going clockwise. And right at that one point where the two directions meet, you have this one isolated attosecond pulse. And the spectrum of that ends up being much smoother. So you can see here that you have all these harmonics that's showing up here. On the right, this is very smooth. And if you look on the bottom right here, what you get is an isolated attosecond burst from about the 40th harmonic order to about the 70th harmonic order. And that's how to create an isolated attosecond pulse. Is one of the ways to do it. A way that I worked on is called the attosecond lighthouse. And so what this does is you have a series of these attosecond bursts, as I showed before, but then you direct them very, very, very quickly, like you would have a lighthouse as it sweeps out its beam. And so it starts off that they're all compact and they overlap, but then as they propagate, they go farther and farther apart until when they propagate far enough away, they're actually separated. And so each one of these pulses here is an attosecond burst. And so as I showed before in that previous slide, you create a series of attosecond bursts. But what we do is we make each burst go in a slightly different direction, and as they go in a slightly different direction, then we get to we can control them, and they can be spatially separated. Well, how do we do this? This is, as I said, this is the attosecond lighthouse. We come in with a really, really, really broad spectrum. We set up two prisms that are slightly misaligned. So instead of compressing the pulse like we would have before, what we actually have is spatial separation. And so at the top of this pulse, we have blue frequencies, and at the bottom of this pulse, we have red frequencies. And so because of that difference in wavelength, you know, the red is longer than blue, that they're actually slightly tilted from one another. And in these black and blue pulses here, these are the attosecond bursts. And so you can see at the back that this one's kind of directed downwards, and at the front, this is directed upwards. It's not a huge separation, but it's just enough that you can separate them. And so in the far field, they end up walking something like this, that, you know, you have earlier pulses and later pulses come out in different directions. So it was like pew, 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 which I always thought was kind of cool. And so this resulted in another paper that I did in Nature Photonics that I actually managed to measure these things. It's called with photoelectron streaking, which is really tricky to do. But I managed to actually measure this pulse and this pulse and this pulse separately. So I managed to measure 3 separate isolated attosecond pulses, which was pretty challenging. But I think up to this point, this is still the broadest pulse that's ever been measured by an attosecond measurement. What this looks like spectrally, so we have each of these pulses. So at the front of the pulse, they go upwards. At the back of the pulse, they go down. And so you can see if we have this spectrum, we have one pulse here, one pulse here, one pulse here, one pulse here. They're not all that well separated. They are separated, but you know, there's a fair amount of overlap, which is what you can see these kind of squiggly lines here, and that's the interference of these sequential pulses. So we'd like to make them more isolated, and so we can use what's called coherent control, where we take the second harmonic of the pulse and we overlap it with that field, and we can see that as we delay that second harmonic, then we can have these pulses here are stronger, and we suppress this pulse here, and we suppress this pulse here, or we change that phase of the second harmonic relative to the fundamental, and we create the other pulses. So now this pulse is stronger, and this pulse is stronger. And so this is called coherent control. And on the right column here, you can see that these pulses aren't that well separated. You might even argue that they're kind of still overlapped here. But when we add the second harmonic, and it doesn't even have to be that strong, it's just enough to perturb the process, that we now have a really strong, distinctive, you know, central peak. In the bottom right case, you can see two distinct isolated attosecond pulses. So this is kind of rehashing this idea that when you're generating these pulses, you have this really, really fast, controlled, strong laser field that's rapidly rotating, and it's creating these attosecond bursts. And when it creates these bursts, these bursts are going to follow what that wavefront looked like of that generating field. And so these earlier pulses go upwards, and these later pulses go downwards. And so you can look at these in terms of the spectrum, just like what I showed here. It's just a reversed image over here. And we can also characterize these things to look like these kind of chirped bursts, which I thought was kind of cool. And we can use each of these pulses for an attosecond pulse. So what I'm trying to do though is create high harmonics from nanoscopic, you know, like particles and stuff like that. And so we started by going to a microscopic level. And so what we had were some electrodes that we managed to bias. And these electrodes had about a 50 micron gap between them. And so the laser beam was focused down to about 50 microns, and there's a 50 micron gap. And if we look at the fifth harmonic, you know, we can see that there's some noise here, or sorry, this was an edge of something. And so we can see that we can generate the fourth harmonic right along the edge, depending on what the polarization is. But when we came to having some electrodes here, so we had an electrode here, so we have an electrode here and an electrode here. The fifth harmonic ends up showing kind of like the outline of these electrodes, but the fourth harmonic, we can actually illuminate these electrodes. So looking at these high harmonics, we can actually see there's a polarization sensitivity, and we can actually control these this even field, these fourth harmonics, by applying the potential of these electrodes. So we could even use these electrodes to generate the 6th harmonic as well. And so if we looked at what a pulse, an electronic pulse looked like, so we'd measure that with the scope here, and we can see, we have very good microsecond resolution, but we could even do this with the 6th harmonic, which would have in principle attosecond resolution, and that's what's going on here. And so we can see that this thing actually falls faster than the scope does. On the right, we wanted something that's even faster. So a scope, is limited to about a microsecond resolution. We wanted something that's even faster, and so we use terahertz radiation. So terahertz radiation is really important because when you go on like a plane, if anybody ever is going to go on a plane again, when you go on a plane and you have to go through those body scanners and you put your arms up, that is a bath of terahertz radiation. And that stuff is lower energy than infrared, but it gets readily absorbed and reflected by metallic objects and also water, so it can see your body. It's also really interesting for condensed matter problems because it turns out that terahertz is where a lot of vibration modes are in material. And so from those of you who might have worked in ultrasound, ultrasound is really, really important in diagnosing materials. You can also use that with terahertz radiation. But it turns out that the fastest way you can measure these terahertz fields is with electro-optic sampling, and that's just given here as EO sampling. And this is given in blue here, and this is the field that you would get with, this is the pulse you would measure with electro-optic sampling. But electro-optic sampling is actually kind of slow relative. It has about a picosecond response. And so it turns out with the high harmonic, with the 6th harmonic, so not that high of harmonic, but a high enough harmonic, we actually have attosecond resolution, and you can actually see that you get this almost instantaneous response here. And so you can see that the 6th harmonic ends up measuring a much shorter pulse than what we get with electro-optic sampling. And so what that's saying is we can have these electrodes here, we can have terahertz radiation, and we can see the 6th harmonic or 4th harmonic that comes out of this and use this to characterize the temporal resolution down to an attosecond timescale with micrometer resolution. So the next generation of things that we want to do is incorporate an atomic force microscope. So atomic force microscopy, this is actually an image that I stole from people from University of Michigan. And I think they were the first ones to do this, and they just did this in like 2017 or 2018, that they took an AFM, so this atomic force microscope, and this has been around for many, many decades. And what they do is, how an AFM works is they have a cantilever, and it's got a shiny back surface, and there's a deflection laser. So a laser, just a really, really weak laser, like a pen laser, some kind of weak laser, hits the back of this, and then you have a really sensitive, really well-designed photodiode. And as this thing moves up and down, then this laser beam moves up and down or left and right, and that tells you what the amplitude of this sample is. And so as you scan over a surface, this thing goes up and down, and that ends up measuring what that surface looks like. And this is called an AFM. And this the tip of this cantilever is on the order of something like 20 nanometers or so. It's not single electron, or it's not single, atomic sensitivity, but it can be really, really small resolution. So it can measure like clusters and things like that. STM, scanning tunneling microscopy, is what can measure single electrons. But anyways, what the group from University of Michigan did just a few years ago was they came in with an infrared source, and they excited this at the same time, and then they saw the coupling between this cantilever and this infrared source, and they ended up measuring the spectrum. And what they found was really, really increased sensitivity to this infrared, for this infrared spectrum when you have this cantilever present. And so what I want to do, and this should be arriving sometime this spring, is having an atomic force microscope, but then we also couple in these femtosecond pulses, and we see how these femtosecond pulses change. And so that gives us actually small changes in femtosecond pulses actually gives us attosecond resolution. And so this AFM tip should have about 20 nanometer resolution, and we should have on the order of sub-femtosecond time resolution. And so that's going to be how fast an electron can actually respond on the size of a very small cluster of electrons. So in summary, we use really strong lasers, and we have those interact with matter. We focus them really tightly, and we have them interacting with matter, and that creates a bunch of new frequencies for us. In order to do interesting experiments, we want sub 100 femtoseconds in duration, and we ideally have something that's shorter than about 5 femtoseconds would be really nice, but it takes a lot of work to get there. With these really short pulses, we can generate even shorter attosecond bursts, and the goal of my research is to combine attosecond science with nanometer scale devices to create attonanoscopy. And I will finish off with a slide of these are kind of the different research directions that we're going in. So I have one grad student who's working on pulse compression. So we have about 120 femtosecond laser source. And we just met with him today, and he was telling me that they have results that are a little bit below 40 femtoseconds. So they managed to get about a factor of 3 in compression. And it would be nice if we could get another factor of 3 out of that. So that is that's part of his project. We of course have to measure these pulses, and so developing a new, more robust waveform measurement technique is what my other grad student is working on. It turns out that when you measure this waveform, you actually completely know the spectrum. So that's kind of like, you know the time really well. It means you know this, well, it's kind of the opposite of what I was saying before. But if you know the spectrum, if you know the waveform really well, you know the spectrum very well. And so by very sensitive waveform measurements, we can measure the spectrum extremely carefully. And if we can make this waveform measurement sensitive enough, that is how we want to incorporate it with this attonanoscopy, because this is going to be a very, very weak signal because we have very few electrons involved with this. And so we need to have very sensitive detection techniques. And so those are the projects that we're currently working on. So if any of this sounds interesting to you, please contact me. I would be happy to discuss this with you. Thank you very much.
So thank you very much, Dr. Hammond. That was an amazing talk. So I guess you have some time for questions.
Yes.
So everyone feel free to either, okay, here, Zach Manson has a question. Earlier, you talked about harmonic generation in the thousands. Are there any practical uses for the 4,000th harmonic, for example? If so, there's a limit at which the use of a very high harmonic is no longer practical. Is high harmonic generation restricted by the Schwinger limit?
I'll answer the first part first. What's the point of generating the 4,000th harmonic? It turns out that it is extremely relevant, and it's extremely relevant for biological processes. And this has been kind of a limitation of XUV. So if you remember before, maybe I can go back to it. When I showed you how harmonics are created, that we have this vacuum chamber, right? So this all has to be done in a really big vacuum chamber because this XUV light gets absorbed by air. It turns out that when you get to high enough energy, so if you think about X-rays, right? So I'm talking about all the stuff that it gets so absorbed, but you say, oh, but if I go to a doctor's office and I get an X-ray, I don't need to have everything pumped out. Otherwise, my face would explode while I'm trying to get my dental X-rays. So obviously you don't need vacuum for X-rays, and you don't need it for visible light. And it turns out that up to about 300 EV is where everything gets really, really absorbed. And above about 300 EV is when stuff stops getting so readily absorbed. So generating above 300 EV allows you to start to access, to start to have transparency again. And so what you can actually do is tune this to what's called the water window. And the water window is around 300 to 400 EV, where the electrons in water no longer absorb this radiation. And so that means that if you actually have biological cells, like if you have biological processes like cells, which are going to be largely consisting of water, and if you have energy that's that high, you would actually be able to image a cell and be able to see the biological processes, like DNA and stuff like that inside of a cell, without having to take it apart first and just look at some molecular chains. And so people are really, really interested in doing this for biological processes. I'm also interested in doing it for biological processes, but I'm looking at doing it in a slightly different way. It turns out water also transmits better at about 600 nanometers, which is actually right in the middle of visible. And so it'd be a lot easier to work in the visible regime and the near IR regime than it is to work in the XUV regime. But I wouldn't have the attosecond resolution that these people would have. And the other question about the Schwinger limit, That is something that people are really interested in doing. Basically, there is a huge push for this from the ELI group, which is, I think, 7 countries in Central and Eastern Europe. You know, Romania, Hungary, I think Croatia is part of it, Poland, I think. They've created these institutes, and they've combined all their resources together to create these really, really powerful lasers, some billions and billions of euros, to be able to create like the world's most powerful laser. And one of the things they want to do with that is test the Schwinger limit. So the Schwinger limit, for those of you who don't know, if you have, basically, if I have this picture here, that you have this electron that's sitting in this atomic potential, and you want it to be separated to, you know, the continuum, this takes a few photons here, right? But you can imagine that the deeper and deeper this electron is in this potential, the more and more photons it's going to take to pull it out. The Schwinger limit is this electron is, instead of being in an atomic potential, it's actually an electron-positron pair, in virtual pair, that well, doesn't really exist. But basically, if you have enough photons to combine them, then you can actually basically create matter out of that. You'd be able to create an electron and positron simultaneously, and you're basically tearing apart the fabric of you know, of space with that. And that's the Schwinger limit. And that's been kind of a goal since, I guess, like the 50s, that people thought, oh, hey, we could maybe do this. But only in, you know, in the past few years have people been able to build these ridiculously powerful lasers. And by ridiculously powerful, I mean 12 orders of magnitude more intense than the laser that I have in my lab. And the one that I have in my lab, you know, can easily ionize air, you know, or your skin, whatever it hits will be ionized. And yet somehow these are going to be so intense that they can actually ionize vacuum, which is just crazy.
Okay, other questions?
Yeah, I'm just having a, sorry, my scroll doesn't work very well. Assuming simplicity depend on 1 micron, 5 micron would be 2 nanometers. Yeah, that's very true. Thanks, Steve. Yeah, what could possibly go wrong with that? Yeah, so that's also a good question. Is what could possibly go wrong with that? People are also using these really strong lasers so instead of for basic science, people can also use these really, really strong lasers for simulating nuclear reactions. So people have, that's also been a pursuit of this, and that's one of the reasons why these lasers were developed in the first place, is that people wanted to try and make fusion reactors. There is arguably some success with that, and it seems like once they became successful, everything became very classified. So instead of being open, you know, all their progress was coming out into the public, and then once they were successful, they haven't published really that much anymore. And I think that's because they were successful. So that's the rumor, at least. Steve, you have a question?
Yeah, I do. I was just going to say, I agree. That's a sign that they're being successful when they're not publishing anymore. So that's usually a good sign when you have those kind of contracts.
Yeah. So these facilities are like billions of dollars, right? And then all of a sudden they don't need to justify their budgets anymore. It would imply that.
Mm-hmm. I was intrigued by the comment you had in your summary slide, which you kind of didn't talk about at all, about the commercialization opportunities. It seems like this could be very attractive to some of your students, and you know, we have not had a lot of these hitherto, but it would be, you know, so great for it. It is normal for physics students to work as graduate students in a lab like yours, and then go off to form these companies and start these things. So could you just talk a little bit? It was in that longer list of goals that you had on what are you talking about for commercialization opportunities? Because commercialized technique. So
that's a great question. That's a great question. So actually, a few people, the first people to be able to characterize femtosecond pulses, both have companies that are based off of this. Well, one has a company, and the other guy has a research program, I guess. It's called the FROG, Frequency Resolved Optical Gating. And this guy loves acronyms. So everything he's developed has been built around amphibious things. So he's got the FROG, the Grenouille, His company is called Swamp Optics. Anyways, he was kind of like the first guy to commercialize measuring these ultrafast laser pulses. And it became important because so many groups were creating these ultra-short laser pulses, but didn't really know how to robustly measure them. And so he came up with a way in the late 90s and created a spin-off company of that. I kind of like my way of doing it. I think it's also simple. I argue that it's even simpler. You can do it in even a single shot. It's also extremely sensitive. And so basically what we're trying to do is, for this waveform measurement, is use this new characterizing technique for these waveform measurements. And I think that would be a way of being able to develop a product, because not only is it for measuring waveforms, as I said, if we can really accurately reproduce the electric field in time, then we can actually very accurately reproduce the electric field in frequency as well, and that's the spectrum. And if we could do this, this should be an extremely robust and sensitive spectroscopic technique that would be comparable to some of the top of the line techniques you can do it, but that are available today. But you can do it in a single shot, so you'd be able to do this at millions of times a second, as opposed to like once a second or something like that. That's kind of the goal of that. And so that's something that I'm interested in doing and interested in developing. And once if we got this working in the lab, I'd be very happy to pursue patents and trying to do a spin-off company with this. So if anybody's interested in kind of working more experimentally and more hands-on stuff, those are kind of the opportunities that we can do in our lab.
Okay, great. Thank you, Dr. Hammond, for a great talk. And I think we're running out of time. So unless there's any other pressing questions, I'd like to mention that Dr. Hammond's email is thammond@uwindsor.ca, and you can just reach him right there. Thank you very much.
Thank you, everybody.
Everyone, please join us next week for Dr. Shao's presentation. Again, a nice Friday evening activity for us.